Okay, we figured out when it happened, now what? We're going to go back 4.5 billion years ago. The atoms that currently comprise the solar system are already around in this part of the cosmos. How those atoms were created, where they came from, we'll think later. Question now is, in what form were they likely to be found? And over the past few decades, we have a pretty good idea of what that form is. The material that currently forms the solar system was probably found in a large molecular cloud. What's a molecular cloud? Well, it's a great big collection of, as we know, mostly hydrogen with some contamination, traces of other elements. It's called molecular if it's cool enough that hydrogen atoms actually form stable bonds and we have hydrogen molecules in it. And inside this molecular, wait a minute, this is already a problem. And it's a problem that I want to pay attention to because this problem will haunt us throughout the rest of the class. The problem is gravity. And the problem is that the idea of a large cloud of hydrogen floating around in space, on the face of it, makes no sense because if you're an atom in the center of a cloud of hydrogen, then of course you're attracted to all other atoms in the cloud, and the net attraction on you, if the cloud is reasonably symmetric, might be zero. Fair enough. But if you're an atom near the edge of the cloud, then clearly the net effect of gravity is to attract you towards the center. Gravity applies a pressure, a contracting pressure, to every object. And whenever we see something in the universe that is not collapsing and crunching down to a point, something must be holding it up. What holds up a molecular cloud? Well, it turns out that a molecular cloud is held up simply by thermal pressures. This molecule near the edge of the cloud may indeed be accelerated towards the center, but on its way there, it encounters other molecules which have random thermal velocities, it scatters off of them, and eventually never gets anywhere. The cloud, the general shape of the cloud, can sustain itself, and we can do a really nice order of magnitude calculation to understand what the conditions in a cloud must be in order for it to sustain itself. And the way we think about it is that if we have a cloud, then we know that the average kinetic energy of a molecule, say, so m would be the mass of a hydrogen molecule in the cloud, is on the order, there may be factors of 2 or 3 that I'm skipping, of k Boltzmann times the temperature. And, on the other hand, the typical gravitational velocity associated to this cloud can be estimated from the escape velocity. If a molecule is moving with the escape velocity, then it's not really bound to the cloud, it can escape, and the escape velocity we computed is again on the order of Newton's constant times the mass of the cloud divided by your distance from the effective center. So r might be the radius of the cloud, would be a typical number to enter. And now, if this velocity and this velocity are of similar orders of magnitude, then one can imagine that the thermal fluctuations in the cloud are about the same order as the gravitational pressure. This will tell us that the cloud can sustain itself under pressure. This is how molecular clouds survive. The denser a cloud, the higher its temperature must be in order to prevent the gas from collapsing. So now we understand that you can have a molecular cloud sitting there. There is still a problem with gravity, and this is a problem that is unique to gravity in contrast to other forces. And the problem that occurs with gravity is that imagine that through some reason, and we'll talk about it later, this region of the cloud becomes denser. If this region becomes a little bit denser than other regions, then of course the net gravitational attraction everywhere is slightly more directed towards this region of the cloud. If the net fluctuation is large enough compared to the temperature that in fact some significant infall occurs, well then more mass will fall onto this region. This region will become denser still. Becoming denser still, the collapse will be more significant. In other words, once you have a fluctuation or some reason, an additional extra dense region in a cloud, because unlike, say, electromagnetism, where if you charge some region with positive charge, it'll attract negative charges and neutralize itself, an enhanced mass density attracts mass, which increases the enhanced mass density. Gravitational collapse is a runaway process. Even if the cloud is holding itself under thermal pressure, the situation is unstable. If you make a sufficiently large perturbation, the cloud will collapse. And this is what happened to our molecular cloud that led to the formation of the solar system. So what caused one region of the cloud to be dense? Well, we think it was a shock wave created by the explosion of a supernova. In fact, probably more than one nearby, and we'll see how that might have happened again later in the class. This causes the great big cloud to break up into fragments and triggers the collapse of these fragments. The fragment that created our solar system was probably on the order of magnitude of 2 to 20,000 astronomical units in size and with a mass of about 3,000 solar masses. This did not create the solar system. In fact, it created a cluster of between 1 and 10,000 stars. So the conditions that we see in the solar system suggest that the sun was formed as part of an open cluster, like the Pleiades. It's now not bound gravitationally to nearby stars, and so it's not part of a cluster. This cluster has dispersed, and in fact, this is a reasonably recent insight that the sun formed as part of a cluster, and the search is on in the neighboring part of the Milky Way to find the stars that were once members of our cluster. I do not know that there has been success so far. And again, the shock wave triggers, remember it's a sound wave, there's a region of high pressure in the cloud. That region becomes sufficiently dense that gravity overcomes thermal pressure. This is called the Jeans instability. It's the fact that if you have a fluctuation, it will grow. And as we saw, if you have a fluctuation whose mass relative to is related to the temperature by this equation, where big M is the mass of the cloud, say, or the region that's collapsing, and little m the mass of the constituent particles, if you satisfy this condition, then the region will collapse. And this is the Jeans condition, and any object that is not collapsing that's made of gas will have to obey a stability condition against this collapse, and larger objects, the condition might change, but everything in the universe that is not collapsing is held up against gravity by something. That's the leitmotif that I want you to take away from this. So, we have this large molecular cloud and it initiates a collapse. In this simulation, what we're going to see is how the collapse of a molecular cloud looks. On the left, we see the density. On the right, the temperature. There's some region of increased density. The cloud is collapsing towards the region of increased density. Localized regions of high temperature are forming. The time scale here is tens or hundreds of millions of years. We see the beginning of stars forming. We see these explosive supernovae. And we see that after a supernova, there's a local flux of sudden star formation. Look at that big supernova, and then the sudden concentration of star formation near it. So this is presumably what happened to us. The sun was formed as one of these clusters that were generated or triggered by the explosion of a nearby supernova. We'll get back to the star part of it, but first we have our cloud. It's about 2,000 astronomical units to a side, and it starts to collapse. But now let us focus our attention on the region immediately near us in the cloud, immediately near where we are now, so somewhere there. We will zoom in and look at a region of maybe 200 astronomical units or 1,000 astronomical units around where we are now. That region begins to collapse under the weight of its own gravity because the fluctuation makes it too dense for temperature to sustain it. What happens when a cloud starts to collapse? Well, first thing we understand is that as the size of the cloud gets smaller, any random rotation that the thermal motion or whatever might have included is going to get sped up by the conservation of angular momentum, as this demo brilliantly shows. So what the demo showed us is that whatever random rotation was part of the thermal motion of this huge 2 to 20,000 astronomical unit sized cloud, as the cloud collapses, is accelerated, and what we find is that the whole cloud is spinning rapidly. Now, it's not spinning rigidly because it's not a piece of plastic hooked up. These are independent particles of gas, but the net result is the same. The rotation is enhanced. This is the rotation that makes the planets orbit the sun in the same direction as the sun rotates. There was an overall rotation present, and it was enhanced by collapse. This is another important result, which is that objects that are collapsing as they come closer to the center in such a direction that they're coming closer to the axis of rotation, by the conservation of angular momentum, mvr being conserved means that as r shrinks, their velocity, their speed has to increase. These objects have to move faster. This creates a barrier that prevents the cloud from collapsing into its axis. On the other hand, collapse in the direction along the axis, in the other direction, is uninhibited by this, and so the cloud collapses far more readily along the axis than perpendicular to the axis. The net result is that what was once probably a roughly spherical cloud is flattened into a pancake shape. This is the reason that we find the planets all orbiting the sun in roughly a plane. The plane of the ecliptic is the plane perpendicular to the original axis that was randomly the axis of rotation, the net rotation of a cloud. And within about 100,000 years of the initial supernova trigger, the cloud has contracted to a radius of about 200 astronomical units, and it's now flattened into what we call a protoplanetary disk, a cloud of dust and gas. Here is a nice infrared image of such a protoplanetary disk in the Orion Nebula, and here's a sequence of nice Hubble images that show us how this takes place. So here we see an image of Orion's dagger with the Orion Nebula in the center, and as I click, we will go through increasing magnifications. We magnify. Here's a magnified view of the nebula. In the center of the nebula, we find all these dust clouds, and in them we find these cocoons in which stars are formed, and upon magnification, the infrared image shows us very nicely the nascent star in the center, surrounded by a protoplanetary disk. It's happening there. Physics is universal. This is the way it happened here. In addition to spinning up, another process that begins to take place as the solar nebula collapses is a process called Kelvin-Helmholtz heating. This involves the fact that some of the gravitational potential energy liberating by all this stuff falling in towards the center is indeed converted into rotational kinetic energy, but most of it is distributed by collisions into heat, into the random motion of the components around them. So as an object contracts under the form of gravity, its gravitational potential energy is being converted into heat, and the temperature therefore rises. This sets up a profile, a distribution around the disk, where of course the density is largest at the center of the disk and tapers off to the edges, and likewise the temperature, the most compression has taken place in the center, so the temperature near the center of the disk eventually reaches 2000 Kelvin, and when it does, we'll see that a surface, next week we'll see that a surface with a temperature of about 2000 Kelvin sort of stabilizes. The material inside it is the proto-sun. Most of that will eventually be the sun. What's left outside is the remnants that will become the rest of the solar system. And so in the center, the temperature is very high and the densities are rising. And then both density and pressure decrease as you move outside. And so you have this disk with hydrogen, helium, and some other materials in this region where both temperature and density decrease with r, with distance from the center. And this will have some serious impact on the state in which we might find different components of the solar nebula. Farther out, we have essentially very small density, very small pressure, and very cold temperatures. Near the middle, it is hot and relatively denser. Let's see an interesting demonstration of how this affects the situation. One of the important ingredients in the solar nebula is water. Hydrogen and oxygen bind to form water. And remembering that it's, despite the increased density from collapse, under very low pressure compared to the atmospheric pressure we feel on Earth, we need to understand how water behaves in space. And so what we've done here is we've taken some water, colored blue so we can see it, and placed it in a vacuum chamber, and essentially we're simulating the conditions in space. The temperature is room temperature and the water is boiling. We know, anybody who cooks knows that as you go to higher altitude at lower pressure, water boils at a lower temperature. Here the water is boiling at room temperature. Boiling water is converting liquid to water vapor. That requires an input of latent heat. When we boil water on the stove, that heat comes from the stove. Here, as when our sweat evaporates from our bodies, it's coming from the water itself, and that's cooling the water down. We see that the boiling is slowing down because as more and more water evaporates, the water is in fact becoming quite cold, and when it becomes cold enough, what we observe is that the boiling completely ceases, the water has frozen. What we've produced, when we take it out, is an ice puck. Essentially, what we're learning is that at the low pressures obtaining in space, water can exist as ice or as water vapor, but not as liquid water. The answer to the question, is there water on Mars or on the moon or in space, in a silly sense, is no. You can have ice and you can have water vapor. You cannot have liquid water at the low pressures obtaining in space. This is something we're familiar with. For example, carbon dioxide exists on Earth as vapor and as solid, but not as a liquid. It's true for any substance at sufficiently low pressure, and at the pressures in space, it's true for all substances. Cannot resist the temptation to demonstrate that with nitrogen, the major component of air. So here we have liquid nitrogen. It is boiling because the boiling point of nitrogen is negative 100 degrees centigrade. We put it into the vacuum chamber, we evacuate, and again, we see that the nitrogen boils even more vigorously. And as it boils even more vigorously at the low pressures, it's cooling itself down, and like the water, eventually nitrogen freezes. The freezing point is only a few degrees lower than the boiling point, but what we have there is solid nitrogen. What we see in this simulation is the impact that the temperature gradient through the nebula will have on the state of various materials or various of the metals that are present in the nebula. We see that, as we said, the temperature near the center, near the outside of the protosun, reaches close to 2,000 degrees. On the other hand, as one moves farther out, the temperature decreases. And what we see is that as the temperature decreases, some materials over here on the right transition from gas to solid. Notice there are no liquids. Metal oxides and metallic iron, for example, are solid at temperatures below 1300 degrees, and so that is the temperature that obtains near the current position of Mercury. Farther out, where Earth is located, other minerals made of iron and sulfur, for example, are solids, but water is still a gas. Water becomes a solid at a temperature of 175 degrees K, and the line at which water, a much more plentiful material than, say, iron or nickel, because remember that graph of abundances was declining on a logarithmic scale. Water, made up of hydrogen and oxygen, is relatively light elements. They're relatively plentiful. Water becomes solid just inside Jupiter's orbit. Perhaps not a coincidence. And then farther out, ammonia and methane become solid somewhere between Saturn's orbit and Uranus's orbit, and argon and neon, noble gases, are solid farther out. What we see is that as you go farther out into the nebula, there are more solids, and this will have an important impact on planet formation. What we've seen is that the fact that temperature and density depend on distance out in the nebula will mean that the form in which various materials or constituents of the nebula are likely to be found will change. Closer to the center, we only find gases. As you move farther and farther out, more and more of the materials are going to be solids. And we saw that in the center, we're forming this protosun. The protosun will eventually become the sun, the region enclosed within this boundary of temperature 2000 Kelvin. Most of that will turn into the sun, and that, in addition to providing us life farther on, sets a ticking time clock for processes going on in this disk full of gas, and in the outer reaches what we call dust, microscopic particles of solids. The ticking clock is that within about 10 million years, the sun will ignite as a star. When that happens, the stellar wind, the solar wind that we discussed, undergoes a very intense period where for a few million years, the solar wind is extremely intense, a few tens of millions of years. This is called the T-Tauri wind. Stars in this stage are called T-Tauri stars. The sun was once a T-Tauri star, and the stellar wind, the pressure of this stream of charged particles is so large that any remaining gas and dust is completely blown away from the system. And so if that gas and dust is to form planets and whatever else it wants to form, the timing is 10 million years. What hasn't formed in 10 million years is going to be blown away. Gas and dust cannot survive the solar wind, although more heavier, more robust objects are able to survive. Here's a nice demonstration of how things look from the point of view of producing a star. What we're going to do again is write density here. Density is column density, so it is density throughout the depth of the nebula. We're seeing a two-dimensional image, and as time increases, we see both density and temperature increase, and we see in the middle the formation of the protosun. The red line indicates a temperature of 2,000 degrees. This is where the protosun will form, and it's still surrounded by the protoplanetary disk, where soon our planets and us will come into being. We'll start that process in the next clip.